So a few too many people were doing that, but if I'm given this, the limit, if this is true, what's true? Diverges. The sum diverges, right? Yeah. Blah, blah, blah. If this is true, if it converges, then what's the limit?
0.
Now, some of you guys who maybe don't feel comfortable speaking up, you could be sitting there going, dude, it's just what I said. It was 0 and it said it converges. Is that what that says? If it converges, then the limit's 0, right? It's just like, if it's a dog, then it's a mammal. If it's a mammal, is it then a dog? No, right? So if-then statements only work one direction. So I think that's, you guys see this and then you think, oh, limit 0 means converge. No, it's not how logic works, right? It only works that one way. So if the limit is 0, what does that mean? We have to do a freaking test, right? Then we actually have to do work. We're not done. Then we must apply a test. Crap, right? It passed. It didn't. The test for divergence didn't show it diverged, so I gotta see. Oh shit! Now I gotta see if it actually converges, right? Okay, maybe. So not everybody did, but a few people is too many. So I want to really make sure you guys understand that. Okay, I like it. All right. So before I jump into section 11.6, anything left over from 11.1, 11.5, those sections that are still troubling you? Yes?
The alternating series tests?
Yes.
I didn't remember anything from that.
Shit. All right. So there's 3 things to it, but the first one normally is kind of like a given. So if I have this, there's sort of 3 things. One of them's silly. And's got to be positive. Pretty much it's almost always a given. What are the other 2 main things? This one makes complete sense because it's exactly what you would do for any series. The very first thing you would do. Limit has to be 0. Not 8. And then what's the last thing? The most exciting piece? Decreasing. Now, a few too many of you, kind of like if I gave you this, let's say n over n squared plus 2, you say, well, okay, n plus 1 over n plus 1 squared plus 2 is less than n over. Is that obvious? Is that an obvious fact? No, it's not an obvious fact. So I need more than that. This is like a beginning point. If you want to do it this way, then you have to cross multiply, you got to keep going. But what's the other way to do it? Derivative, 11. Now, I understand if you have trouble with, notice something. What is the most common derivative rule that seems to be showing up? Quotient rule, kick ass, right? Everybody, it's like second worst compared to chain. I think everybody hates chain the most, and then quotient's a close second. Does that roughly capture what you guys feel? I don't know. I don't want to speak for you. Other way around? Okay. I got you. I'm with you. But what's the product rule? What's product rule? F prime G. Yeah, and you're giving me some license here, right? We're not going to write the of X bullshit. We're just talking about an idea, right? Okay. Quotient rule, and I talked about this before, when I take a derivative of the function that's on the bottom, doesn't it have a negative power because it's on the bottom? That's why there's a minus in the rule. So when I take a derivative at the top, it's positive because it's not on the bottom. It doesn't have a negative power. Minus when I take a derivative of the G, because it's got a negative power. That would come down. And then this is the weird guy. But oh well. Okay, and again, hopefully your teacher from Calc 1 actually showed you a proof of this. Yeah, okay. So yeah, that has become much more important than it ever was before. Now, real quick, if I wanted to do this guy's derivative, I could all day long make this into a product rule. You guys see that? I just made a product rule. If you do this, you'll actually prove to yourself why it becomes g squared, why it becomes over the thing squared. Do you understand how you're going to get two separate fractions here?
Yeah.
And then when you make like terms,
The denominators would square.
it's going to end up being squared. Yeah. So that sort of like shows you where the quotient rule comes from. But there's nothing wrong with it. That's what I did when I was a student. I learned later in life the importance of quotient rule. It actually makes a lot of things quicker. But I always used to do this, because my teacher didn't really tell us really well the idea behind why the quotient rule the way it was. I always forgot, so I just made it this. Right? Okay. So we have 11.1 through 11.5 in the back, and I gave you that handout. If you didn't get it, I don't know if I have any more with me, but it was a handout that's got all the freaking methods, including two that we haven't talked about yet: ratio test and root test. They were at the very bottom. And at the time I told you, yeah, it's only up to this point, right? That's a really freaking good piece of paper to have, because guess what section 11.7 is? It's just got everything. So just like in chapter 7, wasn't there a section that just threw every derivative rule at you, right? Or integration rule. Right? So this is the equivalent of that for chapter 11. 11.7 is going to be just, here's a series. Tell me what's happening. I said, oh shit, which thing do I use? Right? Today we're going to learn two of the most powerful tests yet. And they're kind of freaking cool. So I'm going to try to kind of lead us conceptually in the direction of what these tests are. Can you guys tell me, let me see what you guys think. What's one of the better series forms to get that's really quick to tell what it's doing? There's a couple. P-series kicks ass, yes? What else should kick ass, but maybe geometric? I love it. So, for example, real quick, nice easy question to start off with. Does this converge here? Yeah, and the really cool thing about this one is, this doesn't happen very often for us, but the answer to what that sum is very easy to calculate, right? It's one of the very few general summation rules that we have. They don't really exist for a lot of just generic series I make up. It's probably really difficult to figure out what the actual full sum is. Okay, maybe. So that would converge because R, 7H, less than 1, yeah. So you can figure out what it adds to, blah, blah, blah. What about, now tell me this. Let me do the same thing, but let me do a little something different. So what we're about to get into, what we're leading up to, is an ability to tell when something, what values of x can I put in? So isn't this, let me see if you guys agree with me. If this does converge, doesn't this entire thing represent a number?
Yeah.
In fact, what number would that be? It would be 7/8 over 1 minus 7, blah, 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 right? We know exactly what the number is. What we're going to get into very soon, just to kind of give the whole thing away, one of the most important uses of series is we'll take a function like sine, right? We'll just take sine of x, and we're going to convert it to series form, but it's going to be an infinite polynomial. Now, even though it's an infinite number, right now we're like, what the shit, Jeff? But that's what we're kind of trying to work towards is, given some f of x, can I make a series form for that? Now, some of you guys would be like, why the shit would you ever want to do that? If you have to calculate sine x by hand, is that easy? And I'm not talking sine of pi over 4. I'm talking of sine of 0.173 and 6. Can you do that by hand? Just check them, right? If you had to, if you really had to, could you figure out x plus x cubed over 3? If I say x is 0.1176, whatever it was I said. Couldn't you sit down and do it, right? X cubed, you do 0.1176 times 0.1176, and then do it again. You could totally do that all day. Yes, you have a way to do it. But if I say, what is sine of 0.1176? Do it by hand. You have all the right in the world to say, no. No, Jeff, no, I don't care, you're the teacher. I'm not going to do this. I'm not. So, that's what this whole chapter is kind of working towards, is an alternate way to write some weird, freaky function in polynomial form. Because what's great about polynomials is their derivatives are easy as shit. I don't care how long they are, the derivatives are easy, right? But if I stop somewhere, I can just throw x in and figure out what it is. I can get pretty close to the actual answer. Okay. So here's our first step in that direction. Is this a number? No. This is a function of x. Because can't I make x something? Can somebody tell me what is the domain of this? Like, what values of x will lead this to converge?
How much 7?
Say again?
How much 7?
Let me ask you this. If something's written in this form, like some constant multipliers times x to the n, what will always work is 0, right? If we make x 0, isn't every term 0? And that's going to have it, that arbitrary, that like trivially converges, correct? So you always have 0 as an answer. You're just curious, how far from 0 can I go and still be good? So in this case, what's the highest x can be? More. Yes, it can be less than 8. It can be 7.9. Of course, our downs to what? Negative 8. You guys agree? Because the absolute value of r has to be less than 1.
Right.
So this is very new, but do you see how it's built on ideas we know? We know what makes a geometric series converge. So this is just adding one extra step. Okay, if I wanted to make a series that converged with an 8 on the bottom, what number could I put on the top? Anything between those. I like it. Now, so that's just to kind of get us understanding where chapter 11 is headed. Here. Yeah, that's not that bad because it's built on pretty basic series that we know what's got to happen for them to converge, right? Okay. Now I want to look at geometric in even a different way. So this is number 2. Let's look at number check. Number 3. Yeah. Look at this one again. Let's bring this guy back. Let me make the bottom a little different just because. We talked about that one earlier, right? This guy wants to be geometric. Do you agree? But it isn't really. Okay. Let's look at a few series elements. So can you guys start listing the elements of the series? Something plus something. What's the very first thing? 1/5? 2 over 25? 125? 625, right? So really, the top was growing so slowly. Let's just talk about this conceptually. Is that far away from being truly geometric? Is it really that far away? Like, what would the 100th term be? 100 over 5 to the 100th power. In the eyes of 5 to the 100th power, pretend like it has eyeballs. What's 100? It ain't shit, right? It's basically the same as 1. Okay. So here's a beautiful idea. To be perfectly geometric, you must multiply by the exact same thing each time. To be roughly geometric, so let's see. Let me make a better example here. What about, yeah. Let's see. No, that won't work. Let me think. Let me make a nice one. Cheat a little bit. If I'm trying to make one up that's going to go sideways. Yeah, there we go. Perfect. Okay, yeah, that works. That probably would work. But let's do this, just because. That's basically the same as what we just did. Yeah, it would probably work. Yeah, it would work. Okay. Okay. If I have a geometric series, if I write it like this, for example, if I wrote a geometric series like this, 2 5th, 6 20th, 18 80th, can anybody tell what R is?
3/4.
How did you get that?
It's a common ratio.
Yeah, common ratio. Beautiful way to say it. That's why we gave it an R, right? So you took like one of them divided by the one before it. Does it really matter? If I told you what the 21st and 22nd elements were, and I told you it's geometric, couldn't you figure out what the R is? You just take A22 divided by A21, right? So in general, couldn't I just take one divided by the one before it?
Yeah.
And then I might as well do this, because it's absolute value. So what's got to be true about this? If it's geometric, this has got to be less than 1, right? Let me let that sit with you for a minute. If it's geometric, no matter which element I divide by the one before it, it's going to equal the R, right? And as long as that's less than 1, converges. I like it. So look at this one. Let's see if this is something that pops out. Well, all right. It'll be about the same. We could do the one we just, no, let's do this. Is this geometric? No. When n gets to like 1 billion, 3 to the billionth power versus 1 billion cubed. Right now, of course, that's kind of big, but do you understand how 3 to the 1 billionth power is a shit ton bigger than 1 billion cubed? Does that make any sense? It's a shit ton bigger, right? So eventually this thing doesn't even care about the top. Eventually it looks like it's just being divided by 3. It's just being multiplied by 1/3. How do I, so this test we're about to develop is a way to see, in the long run, even if the series isn't perfectly geometric, it isn't perfectly always multiplied by 1/3, does it eventually look like it's dividing by, or I'm sorry, multiplied by 1/3? Is it become geometric in the long run? So how do we do that? We do basically this, but I say in the long run, right? So I want to set this up, but I want to take the limit as n goes to infinity. I really want this to make sense. If that is a finite number, right, from 0 to infinity, some finite number, right? Then I can check to see if it converges. What would have to be true in order for it to converge? That number would have to be less than 1, because it would represent R. The series is not geometric, correct? But we are seeing in the long run, what does it look like it's multiplying by? So let's try it. What's AN? I give you AN, right? What's AN? N to the third over 3. 3 to the, what's AN plus 1?
N plus 1 over 3 to the n plus 1.
I love it. So let's see what this looks like if I set up this thing. By the way, not surprisingly, what do you think we would call this test? We just set up a ratio, so it's called ratio test. because math people were not very creative. And we made a ratio. We'll call it ratio test. So now, I take the limit. This thing goes infinity. Now we've done this kind of thing before, what I'm about to do. So many of these are already fractional to begin with. I'm going to divide fraction by fraction. I'm just going to multiply by the reciprocal right off the bat, just to be nice to myself. We've done that before. So I'm going to write an plus 1 times the reciprocal of an. Now, please, dear God, don't multiply this shit out. Can anyone tell me what the limit of the ratio of those are? What are the degrees? Are the degrees the same? So what's their limit?
Ratio
1. So now I just got to worry about these. Do you see what I just did? Look for that shit. If it's polynomial in nature, don't multiply any of that shit. You should be able to tell what the limit's going to be. Because that's all I care about right now is the limit. And what's left in here? Anyone know what that reduces to?
So
1 to the n plus 1.
You ready? So 3 to the n. When do you add powers? Multiplying bases. So 3n times 3 to the first, these times. So that is 1/3. So when n gets freaking huge as shit, to get from one term to the next, I'm fundamentally multiplying by 1/3. In fact, let's try that out. Somebody help me. Get your calculator out. What is 100,000 cubed over 3 to the... Oh, shit, your calculator's not going to handle 3 to the 100,000. Well, let's see. I don't think it's going to handle that. Poor little dude. Or dudette, or... whatever it wants to be. Let's see. Yeah, overflow. Okay. So let's be a little less dramatic, Jeff. Let's try 100.
yeah.
Does it work?
Mm-hmm.
All right, sweet. So what do you get? Again, 1.94 times 10 to the negative 42, right?
Yeah.
All right. So let's try 101 cubed over 3 to the 101. What do you get?
6.66 to the 43rd.
All right, now real quick. Stay with me. Which one of these is smaller? This one's smaller, right? Because it's out one more place. You with me? Okay. Try to do this, right? Do 1.94 times 10 to the, which real quick, on your calculator, if you have a graphing calculator, do you guys know where the times 10 to the button is? There's actually a times 10 to the button. Do you see your comma? Your beautiful punctuation that's on your calculator? You guys see the comma. Do you see above it, it says EE? EE means times 10 to the. So if you just hit second comma, negative 42, which way do we want to go? Yeah, I think so. No. Yes, all right. Divided by 6.637 EE negative 43. It should be about 3. Yeah. I kind of divided the other way around. So the bigger the inputs get into this series, the more it's as if the next term, you just have to divide the one before it by 3. Just have to multiply by 1/3. That's what this process comes up with. So when I learned Calc 2, my teacher never really explained why the requirement was this. He just stated, yes, it's got to be less than 1. He just stated that. One of the easiest series for us to deal with is geometric, right? You guys all told me. P series is a little bit easier. Geometric's the next easiest. And that's what this is built on. It's just saying, what does it look like in the long run? Am I multiplying by to go from here to here? And if that multiple is less than 1, it's basically becoming a geometric series convergent. So if this equaled 5/4, what would be true?
Divergent.
Divergent. It does become like a geometric series, but it's have a multiple of 5/4 greater than 1, diverges. What if this equaled 1? I love it. Inconclusive. You have to use a different test. So if it's less than 1, convergent. Greater than 1, divergent. Equal to 1 sucks, because now you got to do a whole other test, because that one doesn't work. Damn it. Right? Okay, maybe. All right, so let's try another problem out together. Then we'll talk about root test, and then I'll give you the little worksheet. It's got some problems. Let's do one with factorial. That's always fun. What about this dude? Yeah. What do you guys think? Actually, let's make it more interesting. Is that not interesting enough? I don't think so. Let's do this. As you learn more about ratio tests, you might want to look back at some earlier problems we did and realize the ratio test would have made some of them a lot quicker. Will ratio test always work? No. Some of the problems we've done using interval test or other comparison tests, L would be 1 if I tried to do the ratio test. You guys with me? In fact, I'll show you a really easy example of that here in a minute. All right. So what's the steps here?
N+1.
Yeah, do the n+1 term. And you multiply, because I'm going to divide, so I multiply the reciprocal of the given, right, the nth term. Okay. And the really nice thing about these tests is there's no restriction except that no terms can be 0. Why does it make sense that no terms in the series can be 0?
Have a ratio?
Because then at some point, the thing I'm dividing by might be 0, and the whole thing goes to shit, right? Okay. So the only restriction for a ratio test is that your series can't have 0 terms in it, right? Any terms that are 0. How do I simplify this? Yeah, this, you should start to realize this. What do you get when you divide these? 2. So that's 2. Now, how do I work with the factorials? What can I do? There's one of them I could do something with.
N+1
Yeah.
factorial becomes N+1 times factorial.
Beautiful. N+1 factorial is n+1 times n minus 1 forever. So I go n+1 times n forever. You can always just pick off the first few terms and then put an exclamation saying, yeah, keep going. I got what I need. You see how we got what we need? Right? These die. And what's this limit? 0. Now that, I had to be a little careful. I did say this earlier. I kind of wanted to do this to kind of go back and correct this. Obviously 0 is an automatic convergent. At some point, this thing is like multiplying by 0, is what this is saying. I mean, this thing gets so big so fast, it's basically like multiplying by 0 when you get up to 18 billion for n. You guys understand? So 0 is kind of like what I said earlier. It's a trivially convergent series. Yeah. So this so converges. And by the way, I got to be a little more on the nose about my convergent. What kind of convergence is this?
Absolute.
Absolute. I love it. So ratio test has absolute convergence built in.
on this part, how do you know it converges? Because I know it equals 0, but.
Oh, because this is not greater than 1. The only thing, this can't be greater than 1. Yeah. So as long as this is, as long as it equals L and that's less than 1. And why do I not have to be more specific? Because it's absolute value. This is positive, right? Okay. Or 0 in this case.
Can you explain how you get the last denominator of pulling the n factorial?
Oh, okay. So real quick, this is going to happen a lot to us. So if I have like n plus 2, so real quick, what's 7 factorial? 7 times 6 times. Anywhere I want to, I can do that. Anywhere I want to, can't I? Because I'm like, I'm tired, man. And I'll just put a little thing saying to the next person, just keep going. I'm done. So that's the same thing. So therefore, I could pull off. And normally I want to stop here, but it depends, right? That's the same as that. Is that cool? Does everybody see that? This is going to happen a lot to us. We're going to see a ton of factorials. So if you really don't like them, ooh, shit. That's too damn bad. I really hope you guys are cool with them. They're not that bad. They're not terrible things, but you're just not used to working with them until now. So is that cool? Okay. Now, let me throw something else at you while I'm thinking about it. Somebody got this here? So this test, the thing that gets calc students down the most is how do I interpret all the different tests? This test is one of the easier ones. Just remind yourself, ratio test is built on geometric. Geometric, less than 1. Done. It's easy to remember what the outcome's got to be, right? Some of you guys got confused. What is it for integral test? Do you guys remember? When you do the integral, if it meets all the requirements, the intervals have got to be positive. Okay, to integrate the function, it's got to be positive. But once you integrate, the answer's got to be finite. It's got to be between 0 and infinity, right? And then that tells you what happens. Okay. It tells you, what does it tell you, by the way? If you integrate the series, if it's finite, that means the series converges. And if it's not finite, that means the series diverges. Okay. This one, though, the results for this one are built on geometric, and geometric is one of the easier things. So just think of L as being R. It's really what that is. What have I done? Oh, I've done that to myself. Let's see. So look at this. Now that I've established that you're not that used to factorials, let's do one with like a shit ton of factorials. What do I want to do? No, that's fine. Actually, let me do this. You can do whatever you want to, John. That's true. Yeah, all right. Look at that. Just soak that in. So I should have said on that handout that's got all the methods from chapter 11 up to 11.6, I should have said something about these are good for exponentials and factorials. I should say that. Right? Polynomial parts don't bother us, because what's the limit of like n plus 2 over n plus 1? That's 1. See, polynomial parts are easy. They can just be taken care of by themselves. So try to set up this. Don't say anything out loud. Just try to set up what this is going to look like. That's where you got to be really careful. Don't go too far. Just try to set it up, because if you didn't do it right, it's not going to quite work. Okay, let me catch up to you guys. This will be n plus 1 factorial. This will be n plus 1 plus 1, so n plus 2. What's going to be here?
2n
Yeah, it's got to be, you got to replace n with n plus 1, right? So the mistake I always see is this, but it's really that. You got to replace n with n plus 1. This says double n, so I got a double n plus 1. So you're going to see this kind of thing every now and again. You just strictly just take n and replace it with n plus 1. And just simplify what you got, right? Factorial. And then times, of course, the reciprocal of all this shite here. Let's see. Hold it up, put it on this. So let's see what we can do. These guys are nice, right? In fact, you might get to a point where you just know what that is, but somebody see what n plus 1 factorial divided by n factorial is? What is it? No? N plus 1. So let me just show you. N plus 1 factorial is n plus 1 times n times, no, I'm tired, times n plus 2. Now let me just do this side. N factorial, so those will cancel. So n plus 1 factorial divided by n factorial is n plus 1. Because the infinite part cancels. Now again, if you're not quite comfortable enough to go there, just write out what it is and start canceling shit. No big deal. But you're going to do this enough, you're going to start to develop shortcuts for some of these things. What about this guy? This is really what? 2n plus 2. So how do I start to break him down? Let me just write this here. 2n plus 2. So it'll be 2n plus 2 times, same thing we did here. No. 2n plus 2 factorial. 2n plus 2 times 1 less is, what's factorial always? Start with the first thing that give you, multiply by 1 less than that. Multiply by 1 less than that forever. Okay, factorial, we get it. So what the hell am I going to multiply by next?
2n plus 1.
Yes, times
2n.
2n. And I'm going to stop there because it matches with what's up here. Do you guys see that? You take the bigger dude and you shuck some pieces off until you match the other guy, so they'll die. All that infinite shit goes away. Yeah, you're freaking us out. So this one's kind of cool. What's the degree on the top? Does everybody see what the survivors are, right? This guy, this guy, this guy, this guy. What's the degree on the top? If I multiply it out, what would it be?
Squared.
Squared. What's the degree on the bottom?
And squared.
Squared, right? So everybody see that? So what's the rule then for the limit as n goes to infinity if the degrees are the same? Ratio of the coefficients, right? What would the coefficient at the top be?
1.
What would the coefficient at the bottom be?
4.
So it's 1/4, which is
Less than 1.
less than 1. So therefore this converges. What kind of way? Absolutely. You can say absolute convergence, or you can say converges absolutely. Yeah. But whatever kind of emphasis you want. It absolutely converges. Or you can not do any of that. So you can just write it. How are we doing so far? Is that? So there's always two levels to this. There's the concept behind something, and then there's the freaking practical application of that. Yes. So I understand in some classes, and I'm totally guilty of this. There'll be a lot of concept and not enough concrete, because I get all excited about the concept, and I'm like, oh yeah, you guys probably want some concrete. These are some of the concrete shit you're going to see. You're going to see factorials. You got to know how to work with them. These are a little weird. You got to remind yourself. You got to replace that with n plus 1. So whatever's there is going to affect the whole damn thing. If I would have made a mistake and not done that, and just had 2n plus 1, that wouldn't have been there. And I would have thought this limit was infinity, because the top degree would have been higher then, right? Do you guys see that? So it's really easy to get a completely wrong answer if you don't treat this thing correctly. Poor little dude. Yes.
I might have just missed it, but in the top portion it's n plus 1 factorial, and then on the bottom of the other portion it's n factorial times n plus 1.
Oh, did I leave him out? Oh man.
Wouldn't that be the same as n plus 1 factorial?
Yeah.
And it would the whole
Well-
thing cancel?
Well, no, I just forgot him. He was here, wasn't he? I got so
Yeah.
excited I forgot him. Damn it. All right.
Cause then
Thank you.
the n plus one.
Alright, that's my fault. I got really excited, I just forgot. So if this is here, right? I just forgot that poor little guy. So let's look at this again. It's not gonna change the results, but it is gonna make it even better. What's the degree of the top?
N. Square.
Second degree.
But,
I know, those will cancel, but you know, you can cancel. Now what's the degree of the top? 1. What's the degree of the bottom? Squared. What's that situation? Is the bottom degree is higher? The limit is 0. Cool. Which is still less than 1. I just forgot the poor little n plus 1. Okay. He's there. I just forgot about him. Alright. So this test, normally when you get here, when you first learn about it, it's a little freaky, but when you see a few examples, it actually becomes better than most of the other tests we've done. This is one you can, and it's because you can sink your teeth into it. Comparison tests, they're a little bit like, whoa, it could be just pick something and try, you know. This test, you can sink your teeth into it. It's a very definitive way to go forward. You do the n plus 1th term divided by n. It's very, you can just do the math at it. It's not vague. As long as you don't forget formula. Okay. Let me talk about this second test. So we have the ratio test, and then we have something called the root test. It's crazy obvious when I want to use the root test. Let me show you. It's not a great one, Jeff. No, it's not a great one. Oh, let me just do this. Change this to this. There we go. What is this inside going to? 0. And what's this going to? Infinity, right? So even the limit would be difficult to do here, just directly of this, to do like a test for divergence, right? So thankfully, and I really want this to make sense why this is a lot like the ratio test, in a geometric series, like if R was 1/5, it would go 1, 1/5, 1/25, right? So if I take the nth root, so if I have 1/5 to the n, and I take the nth root of it, won't I uncover what R is? Very directly, right? Stupid directly, even better than dividing two sequence elements. This is not geometric, but do you see how it's trying to be geometric? For any value of n, this kind of looks geometric, but it's just that n keeps changing, so it's not really geometric. Do you see how it's crazy obvious that what I would love to be able to do is to get rid of that nth power? And that's what an nth root would do. So there are not as many times I'm going to use the root test, because the root test won't help unless everything is raised to the nth power. So I really want to do this. I want to take the nth root of this. So you can imagine if there is no nth power, or if there are parts that don't have an nth power, this is going to suck. I'll have the nth root of like n plus 2. What the shit's that do? I don't know. So I really want to do it mostly for things that have an nth power, because now, what is this? Should be the absolute value, but this is positive. But anyway, what is this?
1 over n plus 1.
Yeah, 1 over n plus 1. And what's that limit? 0. And it's got the exact same interpretation because, again, it's built on the idea of geometric. So whatever number you get has to be, in terms of geometric, what's got to be true about the R? Less than 1. So that's less than 1. Therefore, this thing converges. Cool. Absolutely. Kick ass. Absolute. You can say absolute con. I love it. Count 2 is an absolute con, Jeff. All right. So the root test, what's funny is it's even a more in-your-face, just if geometry keeps multiplying by the same thing, I'm going to take a root to see what that thing is. So if I take a root of this, I see effectively it becomes multiplied by 0 when n gets really, really big. This is basically multiplying itself by something really stupid close to 0. Maybe. Okay. So let me let you guys try this real quick, and then we'll call it a night. So I've got notes on the ratio and root test, and I got a couple problems for each. So go ahead and try out the 5 problems on there. See how far we can get. By the way, if you see a -1 to the end, why does that not bother you at all? Because what's the very first thing you do in these 2 tests? That's your value. So that just basically disappears, right? We'll do the last 2 next time. So let's see. So all the instructions would say is test this for convergence. Right? So now root test and ratio test are both possible things you could try. If you apply either ratio or root and the answer is 1, you got to use a different test. It doesn't mean it just is like, I don't know, right? So limit as n goes to infinity. What we go in here?
N plus 1 over n.
Yes. Be more specific.
2n plus 1 over n plus 1 factorial, then n factorial, and then 2 power n.
Kick ass, right? So this is the next term times the reciprocal of what they gave us. This, of course, is gone because the absolute value. Don't throw him in there and freak yourself out. Here's where a bunch of shortcuts could happen, but I'll do it the long way. This is 2 to the n times 2, n factorial, over, what can I do with this guy?
N plus 1, n factorial.
Good. And of course he is fine because he's going to die there, he's going to die there, and this limit is 0, which is
Absolutely.
less than 1. So be really careful. Some of you guys were like, okay, I can't remember off the top of my head. The limit is 1/5, so therefore it can be no. So you got to say the test. The test is it's got to be less than 1, right? You got to show me that. Not it has to be 1/5. I'll be a dork and I'll say, does it have to be 1/5? No, 1/5 is less than 1. There's the test. Now I know it converges. Absolutely. So what about this second dude? Now, I'm being a little evil. Does any of you guys notice what would be an easier test to apply? I'll take 2 answers. Geometric, and also one we just learned. Isn't everything to an nth power in there?
Yeah.
Root test, okay. But I'm asking you to do the ratio test because I'm an asshole. Limit. So it's going to be, what's going to happen up here?
2.
3n plus?
3.
Yeah, 3 times n plus 1, so just 3n plus 3. That is the easiest place to make a really simple mistake. Okay, and that would totally change the answer to this. Over 7 to the n plus 1, thank you 7. And then of course I just flip this guy. What happens here? When do I add powers? When I was multiplying the bases. So you can always do that. And then of course down here it would be same idea, 7 to the n times 7. And now I got a bunch of stuff that'll cancel. Die. So what's this limit? 8 over 7, which is greater than 1, so it diverges. No need to say absolutely. Right? Absolutely. Right. How's everybody so far? Is that? So do you guys? Does anyone agree with me that ratio test seems to be a little more straightforward? Yeah, I like it. Well, you know I'm going to do stuff to it, but I won't do that. I'm going to start. But at the moment, I can't just let it be nice. I got to come at you with other shit. Oh. Okay. This one's a little freaky, but to be nice to yourself, what does something squared mean? It means that thing times itself. It's not a bad idea to rewrite this as n factorial, right? Okay. So then you're being a little careful. The limit n goes to infinity of n plus 1 factorial, n plus 1 factorial over, we talked about this one already, right?
2n plus 2.
2n plus 2 factorial times the reciprocal of what was already there. Okay, so now I can just start. This is a bunch of, it's the weirdest word ever, but I use it a lot. Shucking. I just shuck some shit. I shucked some, all right. I just like that word. It's too damn bad. So like here I can, let's see if you guys agree with me. I can shuck off an n plus 1. So I got n, I can do the exact same thing to this guy. Are you guys feeling more comfortable about how that works? Factorials just kick so much ass. Divided by this guy we did earlier, I got to take 2n plus 2 times 1 less forever. And then a bunch of stuff can cancel. Die, 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 die. Okay. Very violent math, sorry. And now this is what I was trying to get at earlier, but what's going to happen here? Now this time I'm actually going to get what? Because I don't think I've forgotten it this time. I am going to get the same degree here, right? So the answer is 1/4, because this is dead. Yes, dead. Everybody's dead. So this is 1/4, which is, so therefore this is absolutely convergent. Okay. Some absolute con job. Okay. Not bad. So love the ratio test. We'll finish up that one next time. I want all this out early today. Why not? Let me know if you have any questions from the test. Or if you didn't get your test back, come up and get it. And yeah, I'll see you guys next time.